Hi, good morning, ladies and gentlemen. This is G.srinivas, Assistant Professor in Mathematics of dept. Welcome to today's session. The most interesting and beautiful topic, beta gamma functions of mathematics. This beta gamma. Right. In the early 17th century, the research was started on this factorial of a non-negative integers by Professor Charles, and he has done many experiments, and finally Euler, after doing so many researches, this Euler came to a conclusion that the fractional part cannot take the factorials directly, but with the help of some different special functions, the gamma function and beta function, these are two special functions. There is some specific definition for this beta function and gamma function. We will see one after the other these two functions and the related results which were drawn from these functions. First one, gamma function. Now, a definite integral 0 to infinite e power minus x power n minus 1 dx. This is a definite integral as there are limits for this integration where x is ranging from 0 to infinite. This definite integral 0 to infinite e power minus x power n minus 1, this is the definition of this gamma n, where here n is greater than 0. Now, as you change the value of n, this integral value also going to change. And if this definite integral exists, and that existing value, we call it as a gamma function or gamma n. Now, if you take n is equal to 1, this is the simple result, gamma 1. If I replace n with 1, this is going to be integral 0 to infinite e power minus x power n minus 1. In place of n, I am writing 1 minus 1 into dx. This is integral 0 to infinite e power minus x power 1 minus 1 0, x power 0, it is going to be 1 into dx. Now if you apply the integration e power minus x in the interval 0 to infinite, you get e power minus x by minus 1 from 0 to infinite. This is nothing but minus of e power minus infinite minus e power minus 0. This is minus of 0 minus 1, or which is equal to 1. So this is the standard value of gamma 1. Gamma 1 is equal to 1. Right. As n is an integer and this gamma of 1 is nothing but 1. Just now we have derived. Now there is another result, that is gamma n is equal to n minus 1 into gamma n minus 1. N minus 1 into gamma n minus 1. Here n minus 1 is greater than 0. N minus 1 is greater than 0. Now we'll see how this works or the proof of this. And just now we have seen the definition of gamma, integral 0 to infinite e power minus x power n minus 1. I am repeating once again, gamma n according to the definition, this is integral 0 to infinite e power minus x power n minus 1 into dx. Now if you look at these two functions, these are functions of x, function of x. There are two functions. Now when there is a product of two functions of x, we take the integration by parts in our regular integrations. Right. Now this is an exponential function and this is an algebraic function. So in ILET generally we follow ILET concept here in this definite integration. This is for inverse and logarithmic, algebraic, trigonometric and exponential. This is a very simple concept. Now here comes the algebraic. So this is going to be first function and this is the second function. So integration by parts. Now first function, x power n minus 1 into e power minus x, integration of this and applying the limits from 0 to infinite minus integral 0 to infinite x power n minus 1, derivative is n minus 1 into x power n minus 2 into e power minus x by minus 1 into dx. If I apply these two limits 0 and infinite, this is going to be obviously 0 and this is minus into minus, it's plus integral 0 to infinite n minus 1 I am writing out x power n minus 2 into e power minus x dx. This is n minus 1 into this integral 0 to infinite e power minus x as it is. This x power n minus 2 I am writing it as x power n minus 1 into dx. This is nothing but n minus 1 into this. When you compare this with the definition of gamma n, this is nothing but gamma n minus 1. So finally this gamma n I have taken, this I have proved that it is equal to n minus 1 into gamma n minus 1. So this relation we call it as a recurrence relation. Generally writing the nth term in terms of n minus 1 term is a recurrence relation as usual. Here gamma n is equal to n minus 1 into gamma n minus 1. This is one of the results of the relation, or we can say the property of this. Right, now taking this relation or taking this recurrence relation, gamma n is equal to n minus 1 into gamma n minus 1. I am going to prove another result, that is, if this n is a positive fraction, what happens here? Now gamma n, this is n minus 1 into gamma n minus 1. Once again I am applying this relation here for gamma n minus 1. This is going to be n minus 2 into gamma n minus 2. Now if I continue the same repetition, here once again applying n minus 2, this is going to be n minus 3 into gamma n minus 3. If I repeat this process for r times, this is going to be n minus 1 into n minus 2 into n minus 3 and so on, n minus r into gamma n minus r. Only the condition is here, n minus r is greater than 0. Now this is a relation. If you want to find the product, if you want to find the gamma of any fraction, I'll give a counter example. If you take n is equal to some 3 by 2 or 5 by 2, this is gamma 5 by 2. This is equal to 5 by 2 minus 1 into 5 by 2 minus 2 into 5 by 2 into gamma of 5 by 2 minus 2. This is 3 by 2 into 1 by 2 into gamma half. Now this gamma half is going to be root pi. This is one of the standard value. If you want, we can prove that this is 3 by 2 power 2 into root pi. So like this we can find the values of any fractional part, gamma function of any fractional number, gamma 5 by 2, gamma 7 by 2. Same thing we can apply for gamma 7 by 2. Gamma. Now if n is integer, what happens we'll see. Here this case is a fractional part. If n is a positive integer, second case or conditional. If n belongs to z plus. If n belongs to z plus. Now this gamma n is equal to n minus 1 into n minus 2 into n minus 3 and so on up to 3 into 2 into 1. As I told you, n minus r is greater than 0. This is the last one. So this is nothing but n minus 1 factorial. gamma n is equal to n minus 1 factorial. Now if we want to find the value of gamma 10, this is nothing but 10 minus 1 factorial or 9 factorial. Like this, we have developed a relation between this gamma function and the factorial. This is possible only for n being the positive integer. Now if you take the fraction, this is not possible. So when n is a fraction, we have to directly write this gamma n is equal to n minus 1, n minus 2 and so on up to gamma of n minus half. Okay. We can see some more examples of this gamma function. Gamma minus half. I want this function. Find gamma of minus half. Now if I use this relation gamma n is equal to n minus 1 into gamma n minus 1, it may go to for negative values. So what we do, I am taking the equivalent formula gamma n plus 1 is equal to n into gamma n, right? Now this implies gamma n is equal to gamma n plus 1 by n, and this is similar to the above case. This is derived from the above recurrence relation only. So gamma n, now if you put n is equal to minus half, this is going to be gamma of minus half, which is gamma of minus half plus 1 by n is equal to minus half. This is equal to minus half. So this is gamma half by minus half. This is equal to minus 2 root pi. So this is how to find the gamma values of the negative fractions. I'll give another counter example to find the value of gamma minus pi by 2. Gamma minus pi by 2. Now this is, once again I am taking the same formula. Gamma n is equal to gamma of n plus 1 by n. Now if I take n is equal to minus pi by 2, this is going to be minus pi by 2 plus 1 by minus pi by 2. This is gamma minus 3 by 2 by minus 2 by 5, or this is minus 2 by 5. Now once again minus 1 by 2 by minus 3 by 2. This is going to be 4 by 15 gamma minus half, or this is same as 4 by 15 gamma half by minus half. This is minus 8 by 15 into root pi. This is the value of gamma minus pi by 2. And in a similar way, we define the beta function. This beta function is also a function, special function, but this contains two variables, as gamma is a function of single variable. Now beta function is a function of two variables. Now let us take m comma n are two variables. Now this is also defined with respect to definite integral only. If the definite integral 0 to 1 x power m minus 1 into 1 minus x power n minus 1 into dx, if this definite integral is defined, okay, over the limits x is equal to 0 to 1 x power n minus 1 into 1 minus x whole power n minus 1 dx, this definite integral, if it exists, this existing value we call it as beta of n comma n, right? Now let us see some results related to this. The first result or the property is the symmetric property. Beta of n comma n, beta of n comma n is equal to beta of n comma n. As we interchange the positions of m and n, there will be no effect on the overall result, right? Now according to the definition, I'll give you proof for this. According to definition, this is beta of n comma n is equal to integral x is equal to 0 to 1 x power n minus 1 into 1 minus x whole power n minus 1 into dx, right? Now we have seen the definite integration by parts by substitution method. Let us substitute in place of 1 minus x. I am taking y. Let us define, or let us replace or put 1 minus x is equal to y. This 1 minus x is equal to y. If you take the derivative on both sides, this is minus dx is equal to dy, or this implies dx is equal to dy with the negative sign, with the negative. Similarly, when x is equal to 0, this implies y is equal to 1, and when x is equal to 1, this implies y is equal to 1 minus 1 is nothing but 0. So by substituting this, you are going to get integral of y is equal to, when x is equal to 0, y is 1 to 0. X is 1 minus y, so x is 1 minus y power m minus 1. 1 minus x is y power n minus 1 into minus dy. This I am interchanging the upper and lower limits, so this is left with minus, and this minus and minus get cancels. This is going to be y power n minus 1 into 1 minus y power m minus 1 into dy. This is again, when you compare with the definition of the beta function, this is similar to the beta of n comma m. Beta of n comma m. So beta of m comma n is equal to beta of n comma m. This is the symmetric property. Now there are some more properties are there. The equivalent form of beta function is beta of m comma n is equal to 2 times integral 0 to pi by 2, sine power 2n minus 1 theta into cos power 2n minus 1 into theta d theta. This is an equivalent form of the beta function, and beta of m comma n is equal to beta of m plus 1 comma n plus beta of m comma n plus 1. This is another relation, and there is a relation between beta and gamma function. Relation between beta and gamma function. This is beta of m comma n. Beta of m comma n is equal to gamma n by gamma of m plus n. And this is the relation between beta and gamma function. And there are so many applications related to this beta gamma function in our engineering field, and in mathematics also we can solve some of the problems with the help of these gamma functions, and some Laplace transforms we can solve with the help of these gamma functions. And there are so many applications are there in our engineering day-to-day life and engineering field. Okay.